So there are some oxo acids of chlorine. So oxo acids of chlorine, you can see it on the screen. We are having, that is hypochlorous acid, starting from where the oxidation number is +1. Then we are having chlorous acid, which is +3, the oxidation number is. In chloric acid it is +5, and in perchloric acid it is +7. Hypochlorous acid is HClO, chlorous acid is HClO2, chloric acid is HClO3, and perchloric acid is HClO4. We can say that. Similarly, in case of bromine and iodine also, we are having the same thing. The only thing is that in case of bromine and iodine, we don't have that is bromous acid and iodous acid. Otherwise, rest of the acid you have it. That is, you don't have the oxidation number of +3. In case of bromine and iodine, we don't have, because it does not exist. That particular, what you can say, compound, it does not exist. Because it's a bigger atom and it does not exist for that particular purpose. So we can say that. So that is what you find is that here in case of hypohalous acids, hypochlorites are powerful oxidizing agents and are used as bleaching and sterilizing agents. Again I repeat, hypochlorites, which is also called as hypohalites, they are powerful oxidizing agent and are used as bleaching and sterilizing agents. We can say that. Bleaching powder, that is CaOCl2, we can say, is obtained by treating slaked lime with chlorine. We can say that. Like calcium hydroxide, when it reacts with chlorine, we get bleaching powder, that is calcium oxychloride. We can say that. Now bleaching powder is used for bleaching cotton, linen, wood pulp, etc., and is used as a disinfectant purposes also. It is also used for sterilization of water. We can say that. Now chlorides, on the other hand, that is salts of chlorous acid, are called as chlorides. Alright, the salts of chlorous acid, they are called as chlorides. Chlorides, on the other hand, like sodium chloride, NaClO2, are strong oxidizing agent. They are also used as bleaching agents. We can say that. Coming to halic acids and halates. Halic acids means your HClO3, chloric acid, HBrO3, bromic acid, HiO3, iodic acid. They are called as halic acids. We can say that. The stability of the halic acids increases with increase in the number of increase in the atomic number of the halogen. Got it? Noted this point, it's very important. The stability of the halic acids increases with increase in the atomic number of the halogen. They are strong acids and good oxidizing agents. Their oxidizing power is less than that of halous and hypochlorous acid. Their oxidizing power, again it's an important point, their oxidizing power is less than that of halous and hypochlorous acid. You can see it on the screen also, that is +1 and +3, hypochlorous and chlorous, whereas chloric is +5. The salts of halic acids are called as halates. The salts of halic acids are called as halates, HALATES. Halates, we can say that. Salts of halic acids, we can say. Like sodium and potassium chlorate are prepared on the large scale in this way. Potassium chlorate, KClO3, is used in fireworks and safety matches. Now, the salts of perhalic acids are called as perhalates. Salts of perhalic acid. Among the perhalic acids, we have got perchloric acid, HClO4, periodic acid, HiO4, then perbromic acid we are having, that is nothing but HBrO4 we are having. Got it? So in this way, we are having the salts of perhalic acid are called as perhalates. We can say that. They are also strong oxidizing agent, and their oxidizing power follows the order, that is ClO4 minus is less than BrO4 minus, which is greater than IO4 minus. Mind it. ClO4 minus is less than BrO4 minus, and BrO4 minus is greater than IO4 minus. So perbromates are strongest oxidizing agent among all the perhalates. This is because Br single bond O bond present in BrO4 minus is much weaker as compared to ClO and IO bond present in chlorates and iodates respectively. Again I repeat, that is, the bromates are the strongest oxidizing agent among all the perhalates. ClO4 minus and IO4 minus, it is the strongest oxidizing agent. This is because Br single bond O bond is present, which is present in BrO4 minus, is much weaker as compared to ClO and Cl single bond O and I single bond O bond present in chlorates and iodates. Got it? So for hypohalous acid, the acid strength decreases with the decrease in the electronegativity of the halogen atom. In case of hypohalous acid, that is HClO is more acidic than HBRO is more acidic than HIO. More acidic than HIO. Similarly, in case of oxoacids of halogen, with increase in the oxidation number, the acidic strength of the different oxoacids increases. That is, HClO4 is more stronger oxidizing, stronger acid than HClO3. It's more stronger acid than HClO2. Is more stronger acid than HClO. Again, I repeat. HClO4 is more stronger acid than HClO3 is more stronger acid than HClO2 is more stronger than acid than HClO. What I said, the acidic strength of different oxoacids of halogen increases with an increase in the oxidation number of the halogens. Got it? In case of HClO4 it is +7, HClO3 it is +5, HClO2 it is +3, in case of HClO it is +1. So hence, with increase in oxidation number, what you find is that acidic strength also increases. This is about your that is oxoacids of chlorine, which I said you. Now coming to all the halogen acids in particular, HF are corrosive and should be handled very carefully. Out of all the hydrohalic acids, HF attacks glass and hence it is used for itching of glasses. That is, aqua solution of Cl2 and Br2 are called chlorine and bromine water respectively. Alright. Now coming to the anomalous behavior of fluorine. Like other elements of the second period, fluorine also exhibits different behavior in many characteristic compound characteristics as compared to the rest of the members of the halogen family. Main reasons for this abnormal behavior is same thing which you have studied in nitrogen you studied, in what you can say chlorine you studied. Here also in fluorine also the same thing. That is due to its small size, due to its high electronegativity, due to the absence of vacant d orbitals in its valence shell, and due to low dissociation energy of its molecule. Due to these reasons, what you find is that fluorine shows abnormal behavior due to its small size, high electronegativity, absence of vacant d orbitals and in its valence shell, and low dissociation energy of its molecule. Now, what is the abnormal behavior of fluorine? Fluorine is much more reactive than other elements of the group. This is due to very low value of F single bond F dissociation energy. F single bond F bond dissociation energy. What you find is that fluorine is much more reactive than other elements of the group. Means much more reactive than chlorine, bromine, iodine, and astatine. Fluorine exits only in -1 oxidation state in all compounds. Other elements shows in the same group. Other elements in the same group. When I am talking other elements means in the same group I am saying. +1, +3, +5, +7 oxidation state, whereas fluorine exists as -1 oxidation state because it is the highest electronegative element and absence of vacant d orbital in its valence shells. Alright, and the absence of vacant d orbitals in its valence shell, we can say that. So next is what you find is that fluorine has got next you find is that if fluorine has got in spite of being more negativity than chlorine, the negative value of electron gain enthalpy is less than that of chlorine. This is also due to its small size of atom. Due to small atomic size and high electronegativity, fluorine atoms forms hydrogen bonding in its hydrides, while other elements of the group do not form what you can say hydrogen bond in their hydrides. Alright, hydrofluoric acid is a liquid while all other halogen acids are gases under ordinary conditions. Hydrofluoric acid is a weak acid while all other halogen acids are strong acid. Just now I said. This is due to the high dissociation energy of HF, we can say that. Now, as fluorine has the highest electronegativity, it has strong tendency to form ionic compounds. Alright, strong tendency to form ionic compounds. AlF3 is ionic while all other halides of aluminium are covalent in nature. Alright, they are covalent in nature. Fluorine does not form any polyhalide ion, whereas other halogens form polyhalide ions like I3-, Br3 minus, Cl3 minus. This is due to the presence of, absence of vacant d orbitals in the valence shell of fluorine. This is due to the absence of vacant d orbitals in the valence shell of fluorine. We can say that. Clear. Now we have got pseudo halide ions and pseudo halogens. Which are pseudo halide ions? Pseudo halide ions are Cn minus, OCN minus, SCN minus, SECN minus. Alright, and pseudo halogens are noted cyanogen, Cn whole twice, that is Cn single bond Cn, oxycyanogen, OCN whole twice, OCN whole twice, that is we can say OCN single bond OCN, thiocyanogen, SCN whole twice, same way, and selenocyanogen, seleno, SELENO, cyanogen, CYANOGEN, SECN whole twice. It comes from selenium, we can say that. SECN whole twice. Alright, that is selenocyanogen, we can say that. Clear? So in this way, these are the pseudo what you can say halogens. Now why it is said to be as? Some mononegative ions you can see, that is your Cn minus, OCN minus, SCN minus, SECN minus, made up of two or more electronegative atoms behave in the same way as the halide ions do. Behave in the same way as the halide ions do. Halide means Cl minus, Br minus, I minus, F minus. They are called halide. Such ions are referred to as pseudo halide ions, and their corresponding diatomic molecule are called as pseudo halogens, because they show the same properties similar to that of halogens. Because they show the same properties similar to that of halogens. We can say that. Clear? I hope you understood what is pseudo halide ions and pseudo halogens. Now we'll come to the next is the preparation of chlorine. Now chlorine was discovered by Scheele, we can say that, and it was called as oxymuriatic acid. Later on Davy identified the new element and named it as chlorine. Chlorine has come from the Greek word chlorus, which means greenish yellow, and you know that chlorine, the gas, is also greenish yellow in color. We are getting it basically from the rock salt, from salvine, that is your KCl, carnallite, KCl.MgCl2.6H2O, and we also get it from horn silver, that is AgCl, we can say that. So when manganese dioxide reacts with that is chlorine, we get with HCl, we get that is chlorine gases prepared. That is the one which you can see it on the screen, that I have taken manganese dioxide in the round bottom flask, and HCl I am adding it from the top. By the help of Thistle funnel, I am adding HCl from the top. Now when you add HCl from the top by the help of Thistle funnel, what happens is that manganese dioxide, which acts as an oxidizing agent, or it reacts with HCl to form MnCl2 plus water plus chlorine. Now we remove water, that is to remove any hydrogen chloride gas also, which is being passed here. You can see the 2 Wolf's bottle is being taken here on the figure. You see, all of you can look at it on the screen and you can find it out that we have taken 2 Wolf's bottle, 2 mouth bottle, that is called as Wolf's bottle I have taken. In the first bottle I have taken water. I have taken water because to remove any HCl gas which is liberated with chlorine. Any HCl gas, because HCl is highly soluble in water, to remove any HCl. So first I have removed HCl. Then I have taken another Wolf's bottle which contains concentrated sulfuric acid, which acts as a drying agent or dehydrating agent to remove the moisture which is present in chlorine. And finally I have collected chlorine by the upward displacement of air, because chlorine is quite a heavier gas. It is being collected by the upward displacement of air, so to say. In this way we can prepare what you can say chlorine. We can also prepare a chlorine by taking what you can say that is NaCl, MnO2 and conc H2SO4. That also can be done. Rock salt, NaCl, manganese dioxide, conc H2SO4, which gives you NaHSO4 plus MnSO4 plus chlorine plus water. Alright, NaHSO4 plus MnSO4 plus chlorine plus water. We can also prepare it from bleaching powder. Calcium oxychloride, when reacts with HCl, it gives CaCl2 plus water plus chlorine. We can say that. We can prepare from KMnO4 also, or K2Cr2O7 also, oxidizing agent, KMnO4, K2Cr2O7. When it reacts with HCl, you can balance this reaction. You can write it and balance this equation. will give you KCl plus MnCl2 plus water plus chlorine with KMnO4. Got it? I said you KMnO4 plus HCl will give you KCl plus MnCl2 plus water plus chlorine. You can balance it. Similarly, K2Cr2O7 reacts with HCl to give you KCl plus CrCl3 plus water plus chlorine. We can say that. In this way, you can prepare chlorine. There are different other methods which I said you to by which you can prepare chlorine. Alright, we can also manufacture chlorine by Decon's process. This is an old process for the commercial method for the preparation of chlorine, which is not used nowadays so much of, but we can study this. Here what we can do is that we are passing the oxygen gas into the hydrochloric acid, and in presence of Cu2Cl2, which acts as a catalyst, cuprous chloride, and the temperature is around 673 to 723 Kelvin, we get water and the chlorine, and the chlorine gas is being collected in the drying tower. Chlorine gas, we are getting it from the drying tower. The chlorine gas is being obtained. So chlorine obtained by this process is not very pure and is used for the manufacture of bleaching powder. Got it? Clear? So this is I said you this is an old process. It's commercial. It is used for the commercial preparation of chlorine. As I said you, the chlorine obtained by this process is not so pure, and hence it is being used for the manufacture of bleaching powder, so to say. Again, I repeat the process. We are passing oxygen gas through hydrochloric acid in presence of Cu2Cl2 as a catalyst, and temperature is 673 to 723 Kelvin. The product is your water plus chlorine. Now chlorine is being collected from the drying tower. Got it? And it is not so pure, the chlorine is. Got it? Because along with this chlorine, you are also getting HCl gas, you are getting steam, you are getting nitrogen. Got it? So hence for that purpose it is not so pure, the gases. Got it? Clear? And if at all you are heating concentrated sulfuric acid, the drying tower, you are using concentrated sulfuric acid. If at all the temperature of the concentrated sulfuric acid is slightly higher, then also it may decompose into sulfur dioxide, we can say that. So along with HCl, steam, nitrogen, you can get sulfur dioxide also with chlorine. So hence so many impurities are being present here. So hence it is not so pure, this particular chlorine which is being prepared. Then what we do, we commonly use the Nelson cell nowadays, electrolytic process. We take sodium chloride, that is brine solution, we take it concentrated, and we go for the electrolysis. In the electrolysis process, chlorine is being collected at the anode, where the Nelson cell is being used. Nelson cell, it is simply an electrolytic cell which was prepared by Nelson, and hence it is called as Nelson cell. Got it? So in this way we can also prepare chlorine in the large scale. We can manufacture chlorine in the large scale. Now chlorine is neither combustible nor a supporter of combustion. It is moderately soluble in water, and its aqueous solution is called as chlorine water, which is HClO. Chlorine water, it smells of chlorine. On cooling, the aqueous solution gives yellow crystals of Cl2.8H2O. Alright, it is moderately soluble in water. It is poisonous in nature. When inhaled in small quantities, it causes headache. It may prove fatal also if inhaled in large quantities. Chlorine, if it is inhaled in large quantities, it may prove fatal. It may lead to death. Alright. Now it combines with metals and non-metals to form the respective chlorides. We can say that respective chlorides. Now when chlorine in the absence of sunlight, when chlorine dissolves in water, it forms HCl and HClO, hydrochloric acid and hypochlorous acid. Hypochlorous acid is not much stable and decomposes on standing to form HCl and oxygen gas. We are getting it. So chlorine has got strong affinity for hydrogen. It reacts with hydrogen in presence of chlorine in diffuse sunlight to form HCl. Similarly, it reacts with turpentine, chlorine, when it reacts with turpentine, C10H16, which is turpentine, plus chlorine will give you HCl plus carbon. C10H16 plus chlorine gives HCl plus carbon. All this equation you need to balance it. Now you know that excess chlorine when reacts with ammonia, it forms NH4Cl and NCl3. NH4Cl and NCl3 we can form. It forms. Whereas excess ammonia when reacts with chlorine, it forms NH4Cl and nitrogen. We can say that. Now, chlorine also acts as a bleaching action. It bleaches by the what you can say by the process of oxidation, and the bleaching action of chlorine is permanent. It is not temporary; it is permanent. We can say that. And chlorine is used to bleach cotton fabrics and wood pulp. Got it? It is not used to bleach delicate fibers like silk, wool, etc. because they are damaged by chlorine. We can say that they are damaged, easily damaged by chlorine. Got it? I have said you already that when chlorine reacts with calcium hydroxide in cold, it forms bleaching calcium chloride plus calcium hypochlorite CaOCl whole twice plus water. We can say that. Clear? Now you understood what is the manufacture, how it is being manufactured, how it is prepared, and what are the properties of chlorine, I said you. Now coming to hydrochloric acid, it is being prepared from sodium chloride hydrochloric acid. That is when hydrochloric acid, what you find is that NaCl and conc H2SO4, you can see it in the figure, that sodium chloride I have taken, the brine solution I have taken, and from thistle funnel I am pouring conc sulfuric acid. Then HCl gas is being produced. HCl gas, we are what you can do is that we are passing through concentrated sulfuric acid. You can see an empty flask is being taken here. Got it? An inverted funnel is being taken here, and through inverted funnel we are, what we are doing is that we are passing the HCl gas. Why inverted funnel? We have read the funnel arrangement in the lower classes, that why it is being taken, because to prevent back suction of water. Alright, again I repeat, you can see in the figure that HCl which is being produced, it first passed through the empty flask. Then after that it is being passed through inverted funnel, and inverted funnel is being immersed in water. It is just touching the surface of the water. What will happen? Hydrogen chloride will pass through the inverted funnel to form hydrochloric acid. Why this arrangement is used? Because it will prevent back suction of water. It's going to prevent back suction of water. Alright, that is, water will not the cold water will not come to the hot flask, and it will not what you can say, destroy the hot flask. The hot flask will not crack. So prevent the cracking of the hot flask. For that reason also we have provided an empty flask in between. Alright, so if at all the water comes, if the water comes, alright, it will come to the empty flask. It will not reach to the flask which contains sodium chloride, which is hot. We can say that. To prevent that, we have taken an empty flask in between also. Got it? We have done it. So in this way, HCl is being prepared in the laboratory. We can say that. You can collect it also, HCl, in the dry state. You can collect it by the upward displacement of air. Got it? What you need to do is that you remove this empty flask and the water, and you pass the gas through concentrated sulfuric acid, once again HCl gas, and you collect it with the upward displacement of air. Then the pure and dry HCl gas can be collected. You can say that. You can also what you can say, you can you can't dry the gas by using calcium oxide or phosphorus pentoxide. You can't dry it out, because HCl react with it. HCl is acidic and calcium oxide is basic. It reacts with it. HCl reacts with P2O5 to form POCl3 and HPO3. We can say that. It reacts with it. Clear? So hydrochloric acid, we can see that we can prepare it. But here you need to remember one thing, very important thing, that when you are preparing from sodium chloride, the temperature should be less than 200 degrees centigrade. NaCl plus conc H2SO4, it should be less than 200 degrees centigrade, because if it is less than 200 degrees centigrade, then NaHSO4 and HCl is produced. And if it is more than 200 degrees centigrade, then Na2SO4 and HCl is produced. Now what is the difference? Na2SO4 is a hard crust and sticks to the bottom of the flask, and it is very difficult to remove. Ultimately you have to throw the apparatus. It cannot be removed by any of the method. So hence ultimately you have to throw the apparatus. But sodium bisulfite, it's not a sticky substance. It does not stick to the bottom of the flask. It does not stick to the bottom of the flask, we can say that. Moreover, when a reaction is being carried out below 200, alright, what is the use to take the temperature above 200 degrees centigrade? It is economically loss. Economically we are wasting the energy, we can say that. It is not at all economical, the processes. And the thirdly is that at a high temperature the apparatus may crack. When a reaction can be carried out below 200, above 200 means at a high temperature the apparatus may crack. So hence generally we are advised, or the teachers advises in the laboratory preparations, that the temperature of the mixture should be kept below 200 degrees centigrade, because if it is taken above 200 means it's a wastage of energy. It forms a crust, hard crust, which cannot be removed by any of the method, and at a high temperature the apparatus may crack. Got it? So hence it is advised that the temperature should always be below 200 degree centigrade. You need to remember this. We can also prepare HCl by using KCl. Instead of sodium chloride, we can take potassium chloride also, and barium chloride also we can take it. Got it? Instead of rock salt, that is sodium chloride, which you can see it on the screen, I can take potassium chloride, salvine, and barium chloride also I can take it, and prepare HCl gas. It can also be done, it can also be used, we can say that. Now HCl is highly corrosive in nature. It is, and inhaled it causes slight corrosion or burning sensation on the nose, throat and the lungs, we can say that. It is highly soluble in water. HCl is very highly soluble in water. For that reason only the funnel arrangement we are using it, because if directly the what you can say delivery tube is dipped into the water, then what will happen is that the back suction will be created. Because back suction means what? The HCl gas is more soluble in water. Got it? It is more soluble in water, then it is being prepared. The rate of dissolution of HCl, the rate of dissolution of HCl is more than the rate of preparation of HCl. The rate of dissolution of HCl is more than the rate of preparation of HCl, due to which the water, the back suction will be there and it will go to the hot flask. To prevent that, we are doing this particular arrangement, which you can see it on the screen. Now HCl reacts with carbonates to form the respective salt, water and carbon dioxide. It reacts with base like copper oxide, magnesium oxide, NaOH, calcium hydroxide, copper hydroxide, all this bases to form respective salt and water is being produced. It reacts with sulfite and bisulfite also, like Na2SO3 plus HCl gives NaCl plus water plus SO2. AgNO3, that is nitrate, reacts with HCl to form AgCl, a white PPT, and HNO3 is being produced, we can say that. If you are taking excess of ammonium hydroxide, it forms diamine silver chloride, which is soluble, AgNH3 whole twice Cl. AgNH3 whole twice, you put it in square bracket and Cl outside the square bracket. Diamine silver chloride, which is soluble, plus water. Lead nitrate reacts with HCl to form again a white PPT of lead chloride. Got it? Plus HNO3, we can say that. Clear? Just now we studied that HCl reacts with MnO2, PbO2, Pb3O4, KMnO4, K2Cr2O7. All these things, these are the oxidizing agent to prepare the chlorine gas. To prepare the chlorine gas, we can say that. Clear? We are also having several acids, oxo acids of chlorine, which I have discussed with you already. I have told you about it. Clear? So now fluorine is the most reactive with all the halogens. I have discussed about with you that it is very small, a bond dissociation energy of fluorine molecules with the absence of vacant d orbital valence cells. The maximum covalency of fluorine is 1, -1, we can say that. The oxidation number is. Solubility of fluoride is quite abnormal. For example, AgF is soluble in water, while AgCl, AgBr and AgI are insoluble. Among the halide of any element, fluorides have the maximum ionic character. Just now I said you. Fluorine does not form polyhalide ions. I have discussed with you. Due to the above special properties, fluorine is usually called a superhalogen. Yeah, this is a very important point. All this due to the above special properties which I have discussed with you, fluorine for that reason is called a superhalogen. Superhalogen it is known as. Now, next we will come to, that is your interhalogen compounds, we can say that. The next we are going to come to the interhalogen compounds. So halogens you mutually combine together to form a remarkable set of compounds with a general formula X, Y, N, where X and Y are halogens and N is any integer having value 1, 3, 5 or 7. 1, 3, 5 or 7. These compounds are called as interhalogen compounds. Like we can have CLF, we can have BRF, we can have BRCl, we can have CLF3, we can have BRF3, we can have ICL3, we can have BRF5, we can have IF5, we can have IF7. All these are coming under interhalogen compounds. Example of interhalogen compounds, so to say, interhalogen, where two halogen are there. You can see on the screen it is written as XY N also we can say, or X dash N also we can say that, where X and X dash are different halogens, so to say. Now they are neutral molecules. Interhalogen compounds are two or more different halogen atoms combines to form this. They are negatively charged interhalogen anions like ICl2 minus, ICl4 minus, I3 minus, etc., and positively charged interhalogen cations like ICl2 plus and ICl4 plus, etc. Got it? Are being present, we can say that. Clear? So if you see all interhalogen compounds undergo hydrolysis, giving halide ion derived from the smaller halogen, and a hypohalite in case of halite, halate, perhalate, and anion derived from the larger halogen. All interhalogen compounds of XS dash or XY, whatever you can say, type have linear shape because of the diatomic nature. Polyhalide ions like ICl2 minus, IBr2 minus, etc. have 3 halogen atoms and also are linear. Mind it, they are also linear, we can say that. Got it? Interhalogen compounds are covalent in nature, you can write it down. This is due to the low electronegative difference between halogens. They are covalent in nature. All interhalogen compounds are volatile in nature. Most of them, they are unstable, but none is explosive. They are diamagnetic in nature. They undergo hydrolysis when treated with water, like ICl plus water will give you that is nothing but HOI plus H3O plus Cl minus. ICl3 when treated with water plus a water will give you ICl plus HiO3 plus HCl. We can say that. They behave as strong oxidizing agent. Got it? And attack other elements to give a mixture of halides. Interhalogen compounds of the type XY form addition compounds with unsaturated hydrocarbons. Unsaturated. Now for that reason, interhalogen compounds are used as a fluorinating agent like ClF3 and BrF3. These are the uses I am saying you. ClF3 and BrF3 are also used as oxidizer in propellants. Interhalogen compounds are used for the preparation of polyhalides. Interhalogen compounds are used as halogenating agents. Got it? ICl is used in the estimation of iodine number of fats and oils. We can say that. Clear? This is all about your group 17 elements.